Pre-Calculus students, let's get going on this next virtual lesson. For today's lesson, we're going to look at conic sections. This is the unit that we've currently been working through. We're going to go back to the beginning and see how we generate all four conic sections: the parabola, the circle, the ellipse, and the hyperbola. We're not going to spend a lot of time with the slicing of the cone, but what we are going to spend time with is going back to our definition for each of those four. We're going to look at the standard forms for all four. We're going to talk about how do you find the foci, how do you find the directrix. I know those are things that we've not spent a lot of time on this year because of just time constraints, but it is something that I do want you to know. I don't expect there's going to be much on this for the final exam, but it's something I want you to be comfortable with. Finally, after we've gone through the standard forms and graphing and all of that, we're going to go through a few that are not written in standard form. We'll go through the process of completing a square, generating a graph, and we'll wrap up our video. So, let's go back to the beginning with conic sections. The whole idea of conic sections is we're taking two cones. We sometimes call this the double-named cone. You have a cone down here on the bottom, and then you are connecting it to a second cone on top of that. So you have two cones, and we're going to look at different ways that you could slice the cone to generate the four different conic sections, as well as the degenerate cases. We're not going to focus much on the degenerate cases in this video, but I do want you to know that they exist. So let's give it a shot. Okay, so the program that we're looking at right now is called Google SketchUp. It's not something that I use all that often, but it is beautiful and really helpful for the slicing part of conic sections. So what we have right now is we have the double cone, and this program is going to allow me to move things around so that we can see it from different perspectives. And let's start with the circle. All right, so what we've got right now is we have the double cone. This rectangular region, which is outlined in orange or in blue, that is going to represent the plane. That's how we're going to intersect the cone. I usually talk about this as taking your samurai sword and you are slicing the cone. We're making our slice so that it is perfectly horizontal. When I do that, I'm interested in the intersection of the plane and the cone. What I get is this region here in the middle, which is a circle. If I were to take the plane and raise the plane, I'm going to get a larger circle. If I lower the plane, I'm going to get a circle with a smaller radius. If I actually continue lowering the plane to the point where the two cones touch, instead of getting a circle, I'm going to get a point. The point is one of the degenerate cases for conic sections. I could have also sliced the cone down here with the plane, and again, I'm going to get a circle. So the big takeaway from this part is if you have a double cone and you want to generate a circle, you need to make your slice so it is perfectly horizontal. The resulting intersection will give you a circle. Great. Well, so now that we have the circle under control, let's look at the ellipse. To generate an ellipse, instead of my plane being perfectly horizontal, I'm going to have it tilted at an angle. And I've got this set so that the plane intersects the intersects the cone on one side and then comes through on the other side. And the shape that is generated is an ellipse. Some people at the beginning of the unit were calling it the oval, but we know now that it's actually an ellipse. If I were to raise the plane, I'm going to get a longer ellipse. If I lower the plane, I get a smaller ellipse. If I can do this just right, eventually you see the ellipse shrinks down to the point. So again, we have a degenerate case. The degenerate case of the ellipse is also a point. Now let's look at the parabola. In order to generate the parabola, I've got my plane. Again, it's going to be at an angle, but I'm going to have to do this in a very specific way. I want to have it at such an angle that I actually intersect with the top of the cone, not the side. I want it to intersect the top of the cone and then come through on the bottom of the same cone. If I can do this correctly, let's see if I can make this happen. I should be able to move the shape a little bit so that we can see what's going on. And we can see where the plane intersects the cone is going to be this nice parabolic arch. And if I were to move the plane, I would get wider parabolas, I would get skinnier parabolas. But when I'm doing the intersection, I have to intersect at the top of the cone and come through on the other side of the same cone. Let's move on to the hyperbola. All right, so lastly, we're going to look at the hyperbola. So with the hyperbola, the way that it works is we are going to take our plane, which is represented by this blue rectangle that you see moving, and we're going to intersect it with the double cone. Now, unlike the circle, where you slice it horizontally, or the parabola and the ellipse where you slice it at an angle, we're going to slice the double cone so that it's perfectly vertical. When I do that, what you're going to get is you're going to get two intersections. The plane will intersect the top of the cone, it'll intersect the bottom of the cone, kind of looks like two parabolas. That's what we refer to as a hyperbola. If you were to continue pushing the slice, let's say we slice it so that it perfectly intersects the double cone at the point of intersection, and we can move this around a little bit, what you'll see is the degenerate case. The degenerate case of the hyperbola are these two lines that are intersecting at the point of tangency of the two cones. So to summarize, we have four conic sections: parabola, circle, ellipse, and the hyperbola. You have three degenerate cases. One of them is the point. One of them is the intersecting lines. The last one is just a line, and I can't really model that in Google SketchUp, but if you can imagine the plane intersecting the double cone so that it just touches the cone here on the side of the top one, cuts through the center, and down on the other edge of the bottom cone, you'd get a line. That's going to be the end of Google SketchUp. Where we're going to go from here is we're going to look at the definitions, the standard forms, how we generate the graphs. So here we go. So the first and the easiest of the conic sections is the circle. I'm going to read to you the formal definition. A circle is a set of all points in the plane which are a constant distance from a fixed point F called the center of the circle. This fixed distance is known as the radius of the circle. Okay, well, what does that really mean? We're going to pick a point, we're going to call this F, and we're going to select points that are the same distance from this point. So if this point over here, x comma y, is in the plane, and I measure the distance between those two, I want all the points that are the same distance from the center as this point over here. That distance is what we're going to call the radius. You can imagine taking all the other points that are the same distance. I go out in all directions, that same constant distance, and what are we going to get? We're going to get a very familiar shape. We're going to get the circle, although mine looks like a really unusual egg. This point F is what we're going to call the center. This point xy is a point on the circle. The constant difference is r, that's your radius. That's the picture that you need to have in your head. If we had more time, we could derive the standard form of a circle. The equation for all circles can be written as x minus h squared plus y minus k squared equals r squared, where the center is located at h comma k, and your radius is r. So if I was graphing this, I would pick a point, or I'd start at my center, h comma k. My radius is r. I'm going to move r spaces in that direction. This would put me at the point h plus r comma k. I'm going to move r spaces in this direction. This is h minus r comma k. I'm going to move r spaces up. h comma r plus k. I'm going to move r spaces down. H comma k minus r. I could move r in any angle that I want to, but in terms of labeling your graph, in terms of generating a complete graph, what I expect from all of my students, I need to see your center, and I want to see the four extreme points. I like to call them the north, south, east, and west points. North, south, east, and west. That's going to generate a complete graph for you, and we'll do some practice in just a little bit. Let's move on to the next one. Now for the ellipse. Our formal definition of the ellipse is an ellipse is a set of all points in the plane which are a constant total distance from 2 points, F1 and F2, that we're going to call the foci. So let's look at that. I pick 2 points, any 2 points. For now, we're going to call them F1 and F2. I can have another point, and what I want to look at is how far, what's the distance from this point to the first focus. I'll call that D1 for distance 1. I want to look at the total distance from the point to the second focus. And what I'm looking at is I want D1 plus D2 to be a constant. So any other points that are going to be on the ellipse have to satisfy the condition that when I take the distance from this other point to the focus plus the point to the second focus, those new distances have to add up to the same number as the original distances. Once you do that, once you grab all the points that satisfy that relationship, what you're going to get is an ellipse. My ability to draw the ellipse, not so good. Hopefully my ability to explain the ellipse is much better. Any point that I pick this point, which I'm coloring in orange. I find the distance from the point to the first focus. I add it to the distance from the point to the second focus. I'm going to get the same constant sum for every single point on the ellipse. Well, what does that mean? That means that we now get our standard form of an ellipse. Every ellipse that we're going to look at can be written in the form x minus h squared over a squared plus y minus k squared over b squared is equal to 1. The center for these ellipses are going to be h comma k. The a is how far left and right you move from the center of the ellipse. The b is how far up and down you're going to move from the center of the ellipse. So with this first example, let's say the center is at h comma k. A is how far I move to the right and how far I move to the left. So this point will be at h plus a comma k. This point over here will be at h minus a comma k. B is how far up I go, so this will be h comma k plus b. And how far down I move, h comma k minus b. It would be all the same points on this other ellipse. This is definitely not a technical definition. This is one that we've sort of adopted in pre-calculus. This ellipse over here on the left is wider than it is tall. And I'm going to call that a hamburger ellipse because hamburgers are wider than they are tall. That's our hamburger ellipse. With the ellipse, you have 2 axes of symmetry. You have a horizontal axis of symmetry. You have a vertical axis of symmetry. With the hamburger ellipse, the horizontal axis is the longer one, so we call that the major ellipse. The major axis. There's your major axis. And the vertical one is the shorter one, so we're going to call that the minor axis. If we look over here at the second ellipse, we have an ellipse which is a little bit narrower. It's taller. Well, if this one is the hamburger, then this one has to be the hot dog ellipse. With the hot dog ellipse, you still have your center. You move right and left A spaces. You move up and down B spaces. Your major axis is now the vertical one. The minor axis is now the horizontal one. And that is pretty much all the graphing that we have done so far in pre-calculus this year. In other years, we've also talked about the foci. Where are the foci? Well, let me clean this diagram up a little bit. The foci are always going to be located on the major axis. So in the example of the hot dog ellipse, if this is my center, let's say there's one focus, and there's the second focus. They should be symmetric, so let me move those. The points that are on the ellipse, when I take the distance from the two foci and add those together, I'm supposed to get a constant. What we're going to see is that if A is how far right and left you move, and the B is how far down and how far up you go, you can actually use this relationship in the following way. What I'm going to do, here's the center. I want to figure out how far right and left I move to find the foci. I'm going to use the north point as a way to motivate this. I know the distance from the center to the north point is B, right? How far up and down you move. But the point that is on the ellipse, when I take the distance from the point to the second focus, and I add it to the distance from the point to the first focus, what we know is that that combined length is a constant. But what we can actually see is that it's not just a random constant. The length of the combined distance is equal to the length of the major axis. So how long was the major axis? We went right A spaces, we went left A spaces. So the combined distance is going to be 2A. That makes this side over here A. That side is A. We went up B spaces. We actually formed a right triangle. And although we're not used to seeing it set up this way, I'm going to call the distance from the center to the focus C. Well, if you remember the Pythagorean theorem, this is where I think the lettering is a little unfortunate. We're used to seeing a squared plus b squared equals c squared. What we really need to keep in mind with the Pythagorean theorem, you take the length of the leg, this leg squared, plus the length of that leg, and you square it, is equal to the length of the hypotenuse squared. So we'll get that b squared plus c squared equals a squared. You could solve this and get c squared equals a squared minus b squared, or c equals a squared minus b squared. What did we really do? What we just did is we found a way to determine c. C is how far from the center the foci are located. I can find c by taking the square root of a squared minus b squared. If I was looking at the hot dog ellipse, with the hot dog ellipse, the foci are actually located vertically from the center. Well, instead of looking at the north point, we're going to pick the east point. We went A spaces to the right. That east point, I can do the same thing. I'm going to take this triangle and we're going to turn it vertically. The combined distance from the point to the two foci is going to be equal to the length of the major axis. Well, the length of the major axis for the hot dog, that's 2b. So the distance from the focus to the point plus the point to the focus is 2b. So the hypotenuse of my triangle is b. The leg is equal to a. What I don't know, which is c, is going to be the distance from the center to the focus. And I can set up the relationship that c squared plus a squared equals b squared. If I want to solve this, c squared equals b squared minus a squared. So c is going to be the square root of b squared minus a squared. Those are the two equations that you need to keep in mind if you are asked to find the foci of an ellipse and include those. The foci are always, always, always going to be located on the major axis. So for the hamburger, that's going to be horizontal. For the hot dog, that's going to be vertical. I don't expect that this is going to be assessed on the trimester exam. It's not something that we've talked much about. This is definitely for those of you looking for more of a challenge. This was for you. So let's move on to the next conic section, on to the hyperbola. So there's two types of hyperbola. We're going to call this first one type 1. A hyperbola is the set of all points in the plane, the difference of whose distances from 2 points, F1 and F2, called the foci, is going to be held constant. So we're going to look at 2 points in the plane. We'll call this F1 and F2. If this point, x comma y, is on my hyperbola, then by our definition, what we're saying is if I take the distance, d1, the distance between the point and my focus, and then I take the second distance, that's the distance between the point and the second focus. If I subtract those two, I'm going to get a constant. I'm going to get the same constant for all points on the hyperbola. And technically, we should be looking at the absolute value of the distances. So we have this point that satisfies that relationship. Other points along the hyperbola are all going to have to satisfy that same relationship. So if I find the distance, if I pick this point over here, I find the distance from foci number 1 to this point. I subtract from it the distance from the point to the second foci. I'm going to get the same constant. When I look at all of those points together, what you're going to form is a hyperbola. We have 2 kinds of hyperbola. This is the one that we've said, we describe it as she's standing up. This is a hyperbola that makes this shape. We have the other hyperbola, which would be turned at a 90-degree angle. We call that she's laying down. The standard form for a hyperbola that looks like that, x minus h squared over a squared minus y minus k squared over b squared is equal to 1. The way that we would actually generate this hyperbola, our center is, again, at h comma k. The A tells you how far left and right you're going to move from the center. The B tells you how far up and how far down you're going to move from the center. Well, let's look at this diagram because I don't really see what's going on with the A and the B. Well, if my center is over here at h comma k, I can move A spaces to the right, I can move A spaces left. I move up B spaces and I move down B spaces. These are the exact same moves that we were doing with the ellipse. With the ellipse, we would normally connect these 4 points and be done. In order to generate a hyperbola, what I'm going to do is I need to form a rectangular box that connects these 4 points. That's how I'm going to create the asymptotes for the hyperbola. So I've just made my rectangular box that will pass through these 4 extreme points. I'm going to create the diagonals of the box. The diagonals of the box are actually the asymptotes for the hyperbola. What that means is the hyperbola will, as x heads off towards negative infinity, will get closer and closer and closer without ever touching. They're going to get closer to the asymptotes in both directions. As I go out to the right, my hyperbola will get closer to those asymptotes. Now, in order to generate a complete graph, the last pieces that need to be included, you need to show me the center. You need to show me this point over here, that's going to be vertex number 1. And this point over here, vertex number 2, taken together, we call them the vertices of the hyperbola. Depending on when you've taken the course, we'd also want to look at the foci. The foci, we can call this focus number 2, we can call this focus number 1. The foci, there's a way to determine that distance. And I'm just going to tell you that the relationship is going to be this. C is the distance between the center of the hyperbola and the focus in both directions. And so the way I find c squared is going to be equal to a squared plus b squared. So c is the square root of a squared plus b squared. That's how you would determine the location of the foci for the hyperbola. You would start at the center, and if it is a hyperbola where she's standing up, you go c spaces to the right, c spaces to the left. That's where your foci are going to be located. For those of you looking for proper vocabulary, your hyperbola has two axes of symmetry. You have a horizontal axis of symmetry. In this case, that horizontal axis intersects the hyperbola. We call that a transverse axis. You have a vertical axis of symmetry. It goes right down here through the center. Since that does not intersect the hyperbola, we're going to call that the conjugate axis of symmetry. So that is the first type of hyperbola where she's standing up. Now let's look at the second kind of hyperbola where now she's laying down. Call that the conjugate axis of symmetry. So that is the first type of hyperbola where she's standing up. Now let's look at the second kind of hyperbola where now she's laying down. So with hyperbola type 2, it's the same definition. I'm not going to go through the definition again. What is... So with hyperbola type 2, it's the same definition. Hyperbola is a set of all points in the plane. The difference of whose distances from 2 points f1 and f2, called the foci, is a constant. These two fixed points are called the foci of the hyperbola. Exact same definition as before. What is different in this case is instead of the foci being on the same horizontal line, we're going to look at the foci being on the same vertical line. What that is going to do is it's going to change the standard form. It's also going to change the direction of your hyperbola. This is the one where we say she's laying down. What we have now is we have a different standard form. Y minus k squared over b squared minus x minus h squared over a squared. The center for this hyperbola is located at h comma k. The a value, pay attention to the location of the a value. The a is always going to be underneath the x squared. The a is still how far left and right you move. The b is still how far up and down you move. We're going to start at the center. I'm going to move a spaces right and a spaces left. I'm going to move b spaces up and b spaces down. I'm going to draw my box. I'm going to use the box as my guide to draw my asymptotes. Okay, not exactly the best drawn set of asymptotes I've ever done, but the asymptotes are your guide. Because of the standard form, it was a y squared minus x squared hyperbola. She's laying down, so instead of a hyperbola that does this, we're going to take our hyperbola, we'll get closer and closer and closer to the asymptotes this way. It'll do the same thing down here. We still have a conjugate axis of symmetry and a transverse axis of symmetry. They both pass through the center. This time, the horizontal axis of symmetry is what we're going to call the conjugate axis because it didn't intersect the hyperbola. The vertical axis of symmetry is called the transverse axis because that one would intersect the hyperbola. The foci are located always inside the hyperbola. They're going to be located, if this is focus number 1, and this is focus number 2, they're going to be located on the transverse axis of symmetry. The distance from the center to the focus is c. Distance from the center to the other focus is c. And as we've discussed before, we have the relationship that for the hyperbola, c squared equals a squared plus b squared. So c is equal to the square root of a squared plus b squared. I think that just about does it for the hyperbola. Again, don't worry too terribly much about the foci, the vocabulary of transverse and conjugate axes of symmetry. It's good to know, but at the end of the day, you're going to probably be mostly assessed on, do you know standard form? Can you generate the graph? Or, given the graph, can you generate the standard form? Can you locate the center? Can you do all of that? So that's 3 conic sections down. The last one for us to look at is the parabola, and this is probably the one that you're most familiar with from Algebra 2. So for a lot of this, we're going to be able to go quickly, but there are 2 types of parabolas that we need to look at. So let's get started.